Hi all, I am Abhinaya here from Dr. Umayal Ramanathan College for Women and from the Department of Electronics and Communications. And my slide is about alphanumeric codes. Definition of alphanumeric code is it must be able to recognize code that represented number that is 0 to 9, letters that is A to Z, and some special symbols like hashtag, percentage, slash. This is known as alphanumeric code. The code is fully made up of 26 letters, 10 numbers, and some symbols. The characters of alphanumeric codes are 26 letter that is both in upper case and lower case, 10 numeric digit 0, 1, 2 to 9. There are 25 character symbol such as plus, slash, hashtag, percentage, etc. Each and every character is alphanumeric code is represented by a 7-bit code. Types of alphanumeric codes are: there are 3 types of alphanumeric codes. There are ASCII code, EBCDIC code, Hollerith code. ASCII code. The full form of this code is American Standard Code for Information Interchange. This code is used in microcomputer by it is safe organizations. This code represented a characters with a 7-bit codes. For examples, letter A is coded as 1000001. EBCDIC code. This code is used in IPM equipment. The full form is Extended Binary Coded Decimal Information Code. This is differ from ASCII code. This code uses 8-bit for each and every characters. The last 9th bit for parity. Hollerith code. This code is used in punched card. In punched card contains 18 column and 12 rows. Each column have an alphanumeric characters of 12 bits. Transmissions of the code is simple. 12 rows are marked from top as 12, 11, 0, 1, 2 to 9. First 3 rows are called zone punch. Last 9 are called as numeric punch. The picture is partial listing of first code, that is a ASCII code. The first column is called as decimal column. The second column is BCD binary code. The third column is octal. The fourth column is hexadecimal. Thank you so much all who listen my video with patience.
Now we are going to talk about De Morgan's theorem. A famous mathematician De Morgan derived the two most important theorems of Boolean algebra. It is power tools used in digital system design. Two theorems that are an important part of Boolean algebra were proposed by De Morgan. Let us discuss the De Morgan's first theorem and De Morgan's second theorem. Now, De Morgan's first theorem states that the complement of the sum of all the terms is equal to the product of the complements of each term. That is given like this. Here, we consider only two elements A and B. A plus B whole bar equal to A bar into B bar. Here, bar represents complement. So we are going to express this as a diagrammatic representation like this. So here, this left hand side A plus B whole bar can be represented like this. A and B are the inputs given to this OR gate. Then we get A plus B. This A plus B input to the NOT gate, we get A plus B whole bar. That is equal to the right hand side represented like this. Inputs of A and B. Here as NOT gate represents the inverting operation, that the complement of input A and B. So after this NOT gate, the value is A bar and here it is B bar. This will be and get the result finally A bar dot B bar. Now let us prove the truth table. Here A and B, these are the inputs. So 0, 0, 0, 1, 1, 0, 1, 1. These all are the combinations of inputs. So A plus B, 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, 1 plus 1 is equal to 1. We are going to take the inverting operations, that is the NOT gate a plus b whole bar. So 0 becomes 1, 1 becomes 0. So this is the output of left hand side, a plus b whole bar. 1 0 0 0. Now here consider as the right hand side. The inputs of a and b, a's inverting is a bar, b's inverting is b bar. That is 0 becomes 1, 1 becomes 0. Here a bar dot b bar, that is product of two elements. 1 1 1, 1 into 0 0, 0 into 1 0, 0 into 0 0. So now we can say this is the output of the right hand side. So now we compare the a plus b whole bar and a bar dot b bar. So the outputs are equal. So hence the theorem is proved by using truth table. Next we are going to prove De Morgan's first theorem by using Boolean algebra. From this Boolean algebra we know that a plus a bar equal to 1, a into a bar equal to 0. The same statements can be written like this: sum of a plus b whole bar equal to 1, and product of a plus b whole bar equal to 0. In order to prove De Morgan's first theorem, now we are take the statement a plus b whole bar. We need to prove this first statement. Here we can write this a plus b, a set a plus b whole bar can be written as a bar dot b bar. From this De Morgan's first theorem, because we are going to prove De Morgan's first theorem. Instead of this a plus b whole bar, a bar dot b bar is used. So we are going to make sure that the resulted value should be 1. So a plus b whole bar equal to a bar dot b bar here. The next step, using the postulates, this can be multiplied like this. A plus b plus a bar dot b can be written as a plus b plus a bar dot a plus b bar. So we know that a plus a is always 1, then b plus b bar is 1. Here 1 plus any element is equal to 1. So 1 plus b bar is equal to 1, 1 plus a bar is equal to 1. So finally we get result of 1. Next we can prove this second statement also. A plus b dot a plus b whole bar. Using De Morgan's first theorem, a plus b whole bar is replaced as a bar dot b bar. So a plus b dot a bar dot b bar, that can be written like this: a dot a bar dot b bar, then plus b dot b a bar dot b bar. So here a bar is also 0, then b bar is equal to also 0. Finally we get the result is 0. Hence proved the De Morgan's first theorem. The statement can be expressed as a dot b whole bar equal to a bar plus b bar. The product becomes sum. This expression can be represented diagrammatically as a, b are the inputs. Consider left hand side. Here a and b are the inputs. Here it is the NAND gate, means combination of NOT and AND gate. The output of the NAND gate is a dot b whole bar, this is the left hand side that is equal to right hand side. Can be represented like this. The inputs of A and B. Here the NOT gate represents the inverting operation. So we can get A bar and B bar after the NOT gate. Here it is OR gate. We are going to add these two input values A bar plus B bar. So this is the diagrammatic representations. That is the De Morgan's second theorem. Now let us prove the truth table. Here A and B, these are the inputs. So 0 0 0 1 1 0 1 1. These are the combinations of inputs. A dot B. A dot B is multiplication. 0 into 0 0 0 into 1 0 1 into 0 0 1 into 1 1. We are going take the inverting operations, that is the NOT gate A dot B whole bar. So 1 become 0, 0 become 1. These are the output of left hand side A dot B whole bar. Here consider as the right hand side. Here again two inputs A and B. We are obtaining the complementation operation using invert terms. So 0 0 becomes 1 1, 0 1 becomes 1 0, 1 0 becomes 0 1, 1 1 becomes 0 0. So we are going to add A bar plus B bar. Then we can get 1 plus 1 1, 1 plus 0 1, 0 plus 1 1, 0 plus 0 0. So this is the output of the right hand side. So both the outputs are equal. So next we are going to prove De Morgan's second theorem by using Boolean algebra. Here Boolean algebra, A plus A bar equal to 1, A dot A bar equal to 0. Consider A as A dot B. The statement can be written as A dot B whole bar plus A dot B equal to 1. Likewise as A dot B whole bar dot AB equal to 0. These two statements proved by the De Morgan second theorem. So consider the first statement A dot B plus A dot B whole bar. Here we can write this A dot B whole bar as A bar plus B bar. By using De Morgan second theorem, we can write as like A dot B plus A bar plus B bar. We can state the statement like this: A bar plus B bar plus A dot A bar plus B bar plus B. Next, we know that A plus A bar is always 1, then B plus B bar is 1. So we write 1 plus B bar and 1 plus A bar. Here we get the 1 plus B bar value is 1 and 1 plus A bar value is 1. Finally we get the result of 1. Next come to the next statement A dot B dot A dot B whole bar. Here we can replace this A dot B whole bar is A bar plus B bar using second theorem. So we can write like this and then multiply inside we can get AB A bar plus AB B bar. So we can know that A bar is always 0, then B bar is equal to 0. Finally we get the result is 0. So hence proved the De Morgan second theorem. Thank you. Hello everyone, I am Shishmita from the Department of Electronics and Communication from Dr. Umayal Ramanathan College for Women. Now we are going to talk about the topic of parity checkers. When digital data is transmitted from one location to another, it is necessary to know at the receiving end whether the received data is free of error. A simple form of error detection is achieved by adding an extra bit to the transmitted word. This additional bit is known as the parity bit and it decides whether the data transmitted is error free or not. Types of parity checker. There are two types of parity checker, even parity checker and odd parity checker. First one is even parity. In a even parity system, the parity bit added to the word to be transmitted is chosen so that the number of ones in the modified word is even. For example, 101011 has even parity because it contains 4 ones complement. The ASCII code for the decimal digit 9 is 0111001. This would record the addition of a 0 in the most significant place to give even parity in the modified word. Next one is odd parity. Odd parity means an n-bit input has an odd number of ones. The ASCII code for the decimal digit 9 0111001 would record the addition of a 1 in the most significant place to give odd parity in the modified word. Next, it's a truth table of odd parity and even parity. First column is decimal, second column is BCD code, third column is odd parity, fourth column is even parity. We find out the odd parity from the decimal and BCD code. From the 4-digit BCD code, only one number is different, others are same, hence the odd parity is 0. The given 4-digit is same and also the two pair of 4-digit code is same, hence the odd parity is 1. Next, the even parity. The even parity reverse of odd parity. From the 4-digit BCD code, only one number is different, others are same, hence the even parity is 1. Next, the given 4-digit code is same and also the two pairs of 4-digit is same, hence the even parity is 0. This is the truth table of odd parity and even parity. Next, design of parity checkers. The technique of parity checking is the most popular method detecting errors in stored code groups, especially for storage devices such as magnetic tabs, paper tabs, and even core and drum systems. XOR gates are ideal for checking the parity of a binary number because they produce an output when the input has an add parity of ones. An even parity input to an XOR gate produces a low output. A 2-input XOR gate produces 1 at its output only when the number of ones in the inputs is odd. For even number of ones in the inputs, a 0 output is generated. Next, a diagram of parity checkers. First diagram is 4-bit parity checkers. There are 4 inputs W, X, Y, Z, 1 outputs using NOR gate. Next diagram is 16-bit parity checker. There are 16 inputs, 1 output. Thank you.
Good morning to all. I am Deepa Lakshmi from the Department of Electronics and Communication, Dr. Umayal Ramanathan College for Women. I am here to explain about the counters. The counter is digital logic and computing. A counter is a device which stores the number of times a particular event or process has occurred, often in relationship to a clock. The most common type is a sequential digital logic circuit with an input line called the clock and multiple output line. The important characters. First, maximum number of count. Second, updown count. Third, synchronous or synchronous operation. Fourth, free running or self-stopping. Types of counter. Asynchronous or ripple counter. Flip-flop are connected in such a way that the output of first flip-flop draws the clock of next flip-flop. Circuit is symbol for more number of states. Speed is slow as clock propagates the number of stages. Next, synchronous counter. There is no connection between output of first flip-flop and clock of next flip-flop. Circuit becomes complicated as number of states increases. Speed is high as clock is given at the same time. The picture is synchronous and asynchronous counters circuit. Synchronous and asynchronous counter. Comparison chart. Synchronous counter. The counter is clocked in such a way that each flip-flop in the counter is triggered by the same clock signal at the same time. The next is synchronous counter. Only the first flip-flop is clocked by an external clock, which in turn triggers the clock output of the following flip-flop. The circuit diagram of 3-bit synchronous counter. The next picture is a synchronous counter. Application of counters. First, frequency counter. Second, digital clock. Third, time measurement. Fourth, A to T converter. Fifth, frequency divider circuit. The topic is end. Thank you.
I am Abhinaya from the College of Dr. Umayal Ramanathan College for Women and from the Department of Electronics and Communications. Definition of memory. Memory is one of main part of computer and microprocessor based system. It is used to store a lot and lots of data and functions. Classifications of memories are registers, main memory and secondary memory, sequential access memory and random access memory, static and dynamic memory, volatile and non-volatile memory, magnetic and semiconductor memory. Registers, main memory and secondary memory. Through memories are scattered throughout the computer. Those based on the locations and usage are called register, main memory and secondary memory. Registers are available within the CPU to store data and temporarily during arithmetic and logical operations like addition, subtraction and or etc. Main memory of computer usually of semiconductor type and that are available to external to the CPU to store data and program. Secondary memory operates at lesser speed when compared to register and main memory. Secondary memory is of magnetic memory type. These are used to store large quantity of data. The examples of secondary memory is CD, pen drive, etc. The example of register main memory is Intel x86. The example of main memory is ROM and RAM. Sequential access memory and random access memory. Sequential access memory is one in which a particular memory location is accessed sequentially. Random access memory RAM is one in which any location can be accessed in a random manner. Examples for RAM. Semiconductor RAM. The examples of sequential access memory is video cassette. The examples of RAM is computer, DVD, etc. Static and dynamic memory. In static memory content does not change with time. In dynamic memory is content change with time. Dynamic memory cell use the capacitance. Static memory devices require to refreshing and hold data as long as DC power. Volatile and non-volatile memory. Volatile memory lost its stored data when power to memory circuit is removed. Non-volatile memory retains stored data permanently even after the power supply is turned off. Examples for non-volatile: magnetic core memory, read-only memory. Examples of volatile is chip card, etc. The examples of non-volatile: CD, SD card, hard drive. Magnetic and semiconductor memory. Magnetic memories are constructed using magnetic material. For example, magnetic tape, floppy and compact disc. Magnetic recording in the process of storing data magnetically on the surface of tape, disk or drum. Semiconductor memories are constructed out of semiconductor material using LSI and VLSI technologies. For example, read-only memory, random access memory. Examples of magnetic memory is the floppy disk, hard disk, drive, etc. The examples of semiconductors are chip used in laptop, computer, etc. By here I end with my topic. Thank you.